Hey, hello everybody. Let's do some math today. This is our last lesson in our Unit 4 integral unit. And it's kind of a last resort, if you will, for trying to figure out the area underneath the curve. Okay, and it's another type of approximation that we need to talk about. Before we do it, though, I think this is an awesome warm-up to practice with U subs, another type of problem that I think we should be aware of how to do. So let's think about it. If I want to integrate this, you're probably looking at the inner function, 4 minus 9x squared. So you'd be thinking, all right, u is 4 minus 9x squared, so du is negative 18 x dx. Okay? All right, well, here's the thing. This is the uniqueness to this problem. I think this is pretty cool. First of all, there is no negative 18, so we can bring that over. So negative 1 over 18 dx, or dang it, du. Okay. X dx. Okay. So here's the cool thing. So, okay, the negative 1 over 18 can come out, right? The x dx. All right, well, here's an x, and here's 3 x's. So this is kind of the same thing as saying x times x squared, right? So here's the cool thing. I can substitute out dx and one of the x's with the du. So I have the square root of u, du, and I still have an x squared left over. Okay, because I was not able to substitute that out with the x dx. Okay, so this is what we're left with. Whenever I do u sub, we're left with negative 1 over 18, the integral x squared, integral of u du. Okay, so we still have to do something with this x squared. How do I get rid of that? Well, think back to the other way that we did this in the past, where it was just an x. Let's substitute it out using our u equation. Because don't we have an x squared right here? Look what I mean. All right, so we got u equals 4 minus 9x squared. So negative 9x squared can equal negative 4, or x squared can equal 4 over 9. And if I take the square, well, actually, I don't need to take the square root. And as I'm looking at it, I was like, where's the u go? I completely wrote it without the u. You're probably thinking, what the heck are you doing for us? My bad. So I subtract u minus 4, sorry about that, equals negative 9x squared. I was like, where'd the u go? All right, well, anyway, if I divide by negative 9, so I get negative 1/9, u minus 4 is equal to x squared. All right, well, look, here's x squared, so can I not plug this in for x squared? Let's look what happens when I do that. So I got negative 1 over 18, the integral of, instead of x squared, I got negative 1/9 u minus 4, and then the square root of u, or I'll just say u to the 1/2. And this is something I can integrate, right? I can bring the negative 1/9 out. I can make that positive 1 over 162. And then I can distribute the u. So u to the first times u to the 1/2 is u to the 3/2 minus 4u to the 1/2. Okay. All right. Now, if I integrate this, if I add 1 to the power, that's 5/2. So I got 2/5 u to the 5/2 minus, add 1 to this is 3/2 power. So I got 4 times 2/3 u to the 3/2 plus c. Now all that's left to do is plug in what u is equal to, and we'll call it a day with that. U was 4 minus 9x squared, and we are all good. Boom. So that was just another example of doing u sub with manipulating the u equation at the beginning to substitute out all the x's. All right. All right, now let's move on to the trapezoidal approximation. It's our lesson for today. Here we go. Now, there's going to be times, we learned all these integration rules, right? Well, there's going to be times where we cannot evaluate the integral. There's going to be times where the u sub and our techniques don't work. Here's a prime example. The integration 0 to 1 of e to the x squared dx. Okay, well, what if, for instance, I try to do u sub? I get du equals 2x dx. I can bring the 1/2 over. All right, well, where at anywhere can I plug in the x dx? Like, that doesn't help me at all. I have an x left over. What can I do with this x? It doesn't substitute out. So there is no integration technique for this. So whenever you have data that you can't necessarily find a function for or find the integral for, you got to come up with a really good way to approximate the area underneath the curve. Now, in this particular example, we know the only way to approximate so far is doing a Riemann sum. So that's rectangles with the right or left corner on the graph. Recall that if I have an increasing function, right, where they have a right endpoint approximation or a right Riemann sum, that's a good approximation and all, but it's going to be an over approximation if f is increasing. Okay. Well, what about if I chose to do a left Riemann sum or left endpoint approximation with that graph? Well, again, if f is increasing, you can obviously see that this is going to be an under approximation. Right? And if we have a midpoint approximation, okay, there's a little bit more to the guess of whether it's over or under approximation. Depends on the type of function, but it turns out that if it's increasing and concave up, then it's going to be an under approximation. The point I'm trying to make here is that we have left and right and midpoint Riemann sum, and they have their benefits. Midpoint was the most accurate that we had for polynomial type functions, and you can see how it's a pretty close approximation. But there is one more approximation that we did not talk about that we're going to finish up with today, called trapezoidal approximation, which is more accurate than all of Riemann's. So it's pretty cool. Let's think about it. Okay. Let's look at this function. Trapezoidal approximation is just like Riemann sum, but instead of using a rectangle, we're using trapezoids. That's it. Now, you're used to dealing with a trapezoid that looks like this, okay? Makes a shape like this, and I'm going to draw the trapezoid as a right trapezoid, okay? So there's an example of a trapezoid. That's the shape we're going to be using, okay? Remember, like, a trapezoid has a specific height. It has base 1 and base 2. And if you remember that the area for a trapezoid is 1/2 your height, base 1 plus base 2. Okay? All right. Well, what we're doing is we're going to shift this trapezoid upright, where it looks like this. Okay? This is the generic shape that we're going to be using for our trapezoidal approximation. So now when I shift it, you'll see that you have base 1 and base 2 on the left and right, and your height is right here on the bottom of the trapezoid, right? This height right here is on the bottom of your trapezoid. Okay? So keeping that shape in mind, let's look at how that would be on our function here. Okay? All right, let's kind of write it this way. Let's say that the amount of trapezoids I want you to do in this problem, we're going from 0 all the way to this point right here. Let's say I want to use 1, 2, 3, 4, 5 trapezoids. Let's say n equals 5. Okay, that's the amount we're going to have. Okay. Well, this bottom line here, which was kind of the base of our rectangle, that's going to be the height of our trapezoid, as you can see from this picture right here. Now, it's kind of hard to see on these first two trapezoids, but I'll kind of start maybe right here from on the right side. If I were to draw a trapezoid, I'm going to have this as my height. Each base, each corner of the base is going to touch the function. So I have a function right there. It's going to touch right there. And then that's the trapezoidal shape I'm going to use. Like same thing for this trapezoid in the second spot here. Like if I were to draw up one side, it's going to touch the graph. If I draw up to the other side, it's going to touch the graph. And I attach it. Same thing right here. Draw a trapezoid and just connect the two points that are touching the graph. And same thing right here, same thing right there. Okay. So it's the same exact set. As long as you know the formula for a trapezoid, you're going to be completely fine. It's 1/2 your height, all right, and then your base 1 plus base 2 divided by 2. Oh, sorry, not divided by 2, just base 1 plus base 2, like I said before. Okay? So let's talk about where each of these values come from in the function. Okay. Well, your height, okay, is going to be the lengths of these bases here. And remember how we found that for the rectangle? That's b minus a over n, right? That's or another way of saying that is delta x. So we have 1/2 b minus a over n. All right, now the bases. Think about how the bases are going to work. Like if I start off with this base and this base on the far left triangle. All right, let's say that I start off at, I go 0, 1, 2, 3, 4, 5, okay? Well, the first rectangle, or I'm sorry, the first trapezoid is going to be f of 0 for the first base plus f of 1 for the second base. Okay? So that's going to be the area of the first trapezoid. The area of the second trapezoid is the same height and the same 1/2, but instead of f of 0 and f of 1, it's f of 1 for base 1 and f of 2 for base 2. You see what I'm saying here? I'm using this as my base 1, this is my base 2. And then the next one is going to be 1/2 b minus a over n, and then f of 2 plus f of 3. So this value and this value. Okay? All the way up until we get to the very last one. Now, notice a thing here is every single one of these things we're adding together has the 1/2 b minus a over n, so we can actually take that out as a GCF, and then it's just going to be, the remainder is going to be the sums of all of these bases. And notice how this works. The far left trapezoid is using f of 0 once, but all those heights in between, f of 1, f of 1, f of 2, f of 2, they're all being used twice all the way up until we get to the end, to the far right base. So another way we could write this would be equal to 1/2 b minus a over n, and then f of 0 plus 2 times f of 1 plus 2 times f of 2 plus 2 times f of 3 plus 2 times f of 4, and then finally we end with f of 5. So we're using those middle heights twice and the end heights only once, and that's how you write it. So it's just understanding how to use trapezoids and just add up all their areas. Okay? Let's look at an example. Let's actually do one. Okay, look. Find the trapezoidal approximation using the integral and the number of sections. Okay, so we're trying to approximate the area underneath this curve, the 4th root of 1 plus x squared, something we can't do use sub with. Now, we're doing 8 trapezoids. So, like, I don't know what this graph looks like, but if I'm taking the area between 0 to 2, I'm going to have 1, 2, 3, 4, 5, 6, 7, 8 trapezoids. The fourth root, I'm assuming, looks something like this. Okay, so we're going to have 1, 2, look at all the trapezoids we're going to have here. That's ugly. But that's the general idea. Okay? Now, let's write out the formula pretty much. So a trapezoidal approximation with 8 trapezoids is going to be equal to 1/2 b minus a over n to figure out the heights of all those rectangles. So in this case, that would be from 2 minus 0 over 8, b minus a over n. Okay. And then it's going to be f of 0. All right, there's only one of those. That's the starting point, is at 0, plus. Now, the height of the second one, like if I were to go a distance of each height, that's the distance of 1/4 each time. That's how far we need to go for each length, because this is equal to 1/4. So it's going to be 2 times f of 1/4 plus 2 times f of 1/2 plus 2 times f of 3/4 plus 2 times f of 1 plus 2 times f of 1.5, or I guess 5/4, plus 2 times f of 1.5, or 3/2, and then 2 times f of 7/4, and lastly we end with 1 height at the end. So like we have 1 trapezoid and 1 trapezoid that has those n values as a base, and then all the heights in between that, or the bases in between that, are used more than once. So that's why I write it 2 times that way. Now, you're welcome to write it as 8 separate trapezoidal areas and add them together, but this is just kind of writing it in a factored form. Okay? Now, I encourage you to do this. Type this function into your calculator as y1, and then literally type this into the calculator exactly as we wrote it down, so you don't mess up. Type in y1 of 0 plus 2 y1 of 1/4. Write it that way. Okay. But anyway, the approximation we get is 2.422, which is a lot more accurate than like a midpoint or left or right for even the sum. Okay. All right. 18 minutes. Got a couple more. One thing I want to make a note of, and I want you to write down as well, is about the over and under approximation for trapezoidal. All right, look, we have an over approximation for trapezoidal approximation if our graph is concave up. Okay? Think about how the graph looks. I'm going to draw a really concave up graph. Okay? Think about all the trapezoids we would draw with that. You see how my trapezoids are above the function because it's concave up? So that's going to be an over approximation. It's going to be an under approximation, because with Riemann sum, it's all about like increasing or decreasing. But with trapezoid, it's all about like concave up or concave down. It's an under approximation when it's concave down. So like if it looks like this. Okay. Think about the trapezoids I'm drawing. Every single one of those trapezoids is below the function. So that would be an under approximation. Okay. All right, so I wanted to make that note. Now, I only got 2 more I want to do with you. 1, 2. And you can ignore anything past that dealing with the quiz. Now, on the completed notes online, I do have a bunch of other examples of doing U substitution, because I used to give a second quiz in this unit. You're welcome to do those for any extra practice, but for us, we're going to stop at trapezoid. So I only got 2 more. And your delta math is going to involve you doing trapezoidal with an equation and with a chart. I like the chart a lot better. It says the data below represents velocities taken at certain time intervals in miles per hour, and we're going to use a trapezoidal rule or approximation to estimate the distance traveled after 10 minutes. So here's 0 minutes, here's all the way to 10 minutes. This might be a long problem, but this is what it looks like, okay? We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 trapezoids that we're going to add up the areas of. Okay. Now, one mistake that I don't want to make that I have made in the past, and this is rarely happens, but we're talking about the velocity in terms of miles per hour, and all of our time intervals are in terms of minutes, so we should probably change that to hours. So, like for instance, like 1 minute is the same thing as like 1 over 60 hours, and this is 2 over 60 hours, over 60, over 60. So all I'm doing is just converting these time intervals to hours. So really we're going from 0 hours to 10 over 60th hours, or 1/6 an hour. Okay. So the formula is 1/2 our height. Now our height is the length, or our height is the distance from one t value to the next. In this case, that is 1 over 60. That is our delta t, or change in t. Okay. Then, if you, like, okay, for instance, if you just want to do one trapezoid, it's f of 0 plus f of 1. That's base 1 plus base 2. And you're welcome to do that 10 times. But if you take out the GCF and you want to simplify it out a little bit, this is what you're really doing. Okay? You're going to use all those middle numbers twice for each of your trapezoids. So it's going to be f of 0 plus 2 times f of, I guess, v of, or f of 1, plus 2 times f of 2. Dot, 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 right? Okay. Well, since I already know those outputs, I'm just going to go ahead and write those out. So I don't have to worry about writing the f of notation. Okay? So what I have here is f of 0 is 0 plus 2 times 50 plus 2 times 60 plus 2 times 80 plus 2 times 90 plus 2 times 100 plus 2 times 95, 2 times 85, 2 times 80, 2 times 75, and then only 1 of the very last value, because we only have one trapezoid that uses that. Now that's a lot to type in, but take your time, and you're going to get a very accurate approximation. Okay. I ended up getting 12.625 miles that have been traveled between 0 to 10 minutes. Okay. All right, let's try one more pretty straightforward. Example 3 says the function f is continuous on the interval 2 to 8. That's a typo. It's between 3 and 12. That's weird. And has values that are given in the table below. What is the trapezoidal approximation of the integral from 3 to 12 of f of x dx? Here's 3, here's 12. The best way we can approximate that integral, since we're not actually given the equation, is to do an approximation using 3 trapezoids. Now here's the only thing I want you to watch out for. In the last example, all of the heights were consistent. Here, this has got a height of 2, this has got a height of 4, and this has got a height of 3. So we're actually going to have to write out 3 separate trapezoidal areas. So for the first one, it'll be 1/2 times the height 2 times base 1 10 plus base 2 30, plus the area of the second trapezoid is 1/2. The height is 4, and then it's base 1 30 plus base 2 40. plus, and the final one is 1/2. The height is 30, and then base 1 is 40, plus base 2 is 20. All right. Okay, so we have a little bit of practice that you can do with this. I got a worksheet that you can try these problems with on Canvas, and also Delta Math is practicing these pretty good too. So do your Delta Math. Make sure you're good on this, and I'll answer any questions you may have on it on Monday. But we're also going to mostly review on Monday. So I encourage you to look over the review sheet for Monday and try to already come to class with any questions you may have. I'll have the test, like questions breakdown, ready for Monday, and we'll discuss it all then. Okay? All right, guys. Well, I hope you'll have a great day and a great weekend, and I will talk to you later.